will wrap up this week of discrete random variables by giving a list of standard random variables that you would see uh, in text in books all over, which are the Bernoulli, the binomial, the Poisson and the geometric random variables. All of these are discrete random variables. Uh, will give their probability mass function and some of their moments. We will give their expectation and if possible the variance also. So what is the Bernoulli distribution? Bernoulli distribution is the simplest distribution that you can think of, which is they will give the probability mass function of that, which is f of 1 is equal to p and f of 0 is equal to 1 minus p. So this is a probability mass function which can take only two values 1 and 0 and it is parameterized by p. For example, if you had a coin whose probability of heads was p, small p, then that would correspond to a Bernoulli random variable or Bernoulli distribution with bias p. So this p is often called the bias. So if p equal to half, it is an unbiased Bernoulli distribution, but you can have a general p which would be called the bias of the Bernoulli distribution. So this is a pretty simple distribution, can take only values 1 and 0. What is the expected value of, let us say, x? You might see written as x is distributed as Bernoulli p. This might be a statement that you would see, x is a random variable is distributed as Bernoulli p. So by that we mean the probability mass function of x is equal to this. So what is the expected value if x is distributed as Bernoulli p? What is the expected value of x? Well, that is equal to probability of x equal to 1, which is exactly equal to p. So if x is distributed as Bernoulli p, the expected value of x is p. What is the variance of x? We know variance of x is expected value of x squared minus expected value of x the whole square. But x is a random variable which takes values only 1 or 0. So x and x squared are really the same. So ex squared is equal to ex, so which is p. P minus p squared, which is equal to p into 1 minus p. So this is instructive to look at. The average or the mean of x is simply p, but the variance of x is p into 1 minus p. So this is recall we had said variance as the measure of deviation of the random variable from its mean. So if p was either very small or very large, which correspond to p being very close to 1 or very close to 0, the random variable is always going to take either always 1 or always 0. So which means that your variance is going to be low. So if you want to, the value of p which maximizes the variance is the value of p which maximizes p into 1 minus p, and that is exactly equal to half. When p equal to half is when the variance of the Bernoulli random variable is maximized. That is all about for a Bernoulli distribution. Now we have the binomial distribution. The binomial distribution is denoted as binomial of n comma p. And the binomial distribution occurs naturally when you add independent Bernoulli random variables. Let us say you have x1, x2 dot 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 xn are independent Bernoulli p random variables, and you can define x to be equal to sum over I equal to 1 to n xi. Each of these are Bernoulli random variables and they are independent, and you add all of them to get x. In this case, x would be distributed as binomial of n comma p. That is fine, but what is the probability mass function of x? What is the probability mass function of x? Well, f(x) of k is probability of x is equal to k, which is when will, let us to interpret it this way, if you are tossing n coins with bias p, what is the probability that the number of heads is equal to k? Well, there are 2 power n possibilities, right? So there are 2 power n possible coin toss sequences, out of which of them give you exactly k coin tosses, just there are n choose k ways in which you can get exactly k heads, and each of those correspond to a sequence where something like, let us say, k equal to 2 would mean h h t t t t t. H h can be anywhere, it can be for example t t h h t or so on, right. But the key thing to note is the probability of any of this exact sequence happening is that there are k heads and n minus k tails. And these are independent. The probability that you have exactly that sequence is exactly equal to p power k into 1 minus p power n minus k. So, this is why you can see that it is called the binomial distribution, because it contains the binomial coefficients. The n choose k comes from the fact that you can, if you want, you have n coin tosses and you want k heads, you have to choose the k spots out of the n spots. So, there are n choose k ways in which you can do that, and the probability of each of those coin toss sequences is exactly equal to p power k into 1 minus p power n minus k. So, that is your probability mass function of the binomial random variable. Right. What is the expected value of, let us say you have x is distributed as, well, first of all let us check whether it is a valid probability mass function, right. Which means that what is sum over k equal to 0 to n. So, the maximum value the binomial random variable can take is n, right, because even if all the n tosses turn out to be heads, that is the maximum value it can take. So, k equal to 0 to n f of k. What is that? Well, that is equal to sum over k equal to 0 to n choose k into p power k into 1 minus p power n minus k. If you know your binomial theorem, this is exactly equal to p plus 1 minus p power n, which is exactly equal to 1. So, you have that this is a valid probability mass function. So, that is the first property. Then we will move on to expectation. What is the expected value of let us say x is distributed as binomial of n comma p. What is Ex? Here you can use the linearity of expectation, that is Ex is simply equal to sum over I equal to 1 to n Exi. Each of these are Bernoulli random variables. So, which Bernoulli random variables expectation is equal to p. So, this is equal to np. What about variance of x? This requires an important property of variance, that is variance of variance of the sum is equal to the sum of the variance if the terms are independent. If you have variance of the sum of independent random variables is equal to the sum of the variance. And in this case they do happen to be independent. So, variance of x is equal to sum over I equal to 1 to n variance of xi, and variance of xi is p into 1 minus p. So, you have n such terms, put all of that together, you get n p 1 minus p. Sometimes you might see 1 minus p called as q, just npq. That is another standard way. So, that means that we have the mean of the binomial distribution is np and the variance is npq. So, finally move on to the Poisson distribution. The Poisson distribution is a specialized, it can be viewed as a specialized case of binomial distribution. It's the probability of, it's effectively the random variable of a very rare, corresponding to the very rare events. For example, let us say you have a factory manufacturing products. Let us say the failure rate of is, let us say 10 power minus 5, 1 in 10,000 products fails. And let us say you manufacture millions or even tens of millions of products every year. You want to know how many failures happen in a year. This is an example of, you can model this using binomial random variables or binomial distribution, but it is easier to use Poisson because of the very small failure probabilities and very small probabilities p and large number of n, right. So, for example, this is the, if binomial of n comma p, if n is very large and p is very small, this corresponds to a special case which approximates the Poisson distribution. but we can define the Poisson distribution independently. That is, fx of k is probability of x is equal to k, which is e power minus lambda to lambda power k by k factorial. X is distributed as Poisson and the Poisson distribution parameter is lambda. The same way for the Bernoulli distribution the parameter is p, and for the binomial distribution its parameter is by n and p. For Poisson there is a parameter lambda which is a positive value. It can be, it's a real valued number. The probability of, if x is distributed as Poisson of lambda, then the probability mass function fx of k is given by probability of x equal to a, which is e power minus lambda lambda power k by k factorial. You can immediately see that this does sum to 1 as you sum over infinity, right. That sum over k equal to 0 to infinity fx of k. So, this is the first discrete random variable that you are seeing, which can take, it is discrete still, it can take only integer numbers, but it can take arbitrarily high values. So, you can go all the way to infinity. So, sum over k equal to 0 to infinity fx of k is e power minus lambda into sum over k equal to 0 to infinity lambda power k by k factorial. If you know Taylor series, this is exactly equal to e power lambda. This is e power minus lambda into e power lambda is equal to 1. So, this does sum to 1. So, that property is satisfied. What about the expectation and variance? We will just do the expectation of the Poisson distribution. It is pretty easy to do. Let us say x is distributed as Poisson of lambda. What is Ex? Well, Ex is sum over k equal to 0 to infinity k times fx of k, which is sum over k equal to 0 to infinity. We will just make it 1 to infinity because k equal to 0 adds nothing. So, k equal to 1 to infinity k times e power minus lambda lambda power k by k factorial, and k factorial and k cancels to get k minus 1 factorial. So, we will take e power minus lambda outside, e power minus lambda into sum over k equal to 1 to infinity lambda power k by k minus 1 factorial. Let us take just one lambda outside. So, e power minus lambda into lambda into sum over k equal to 1 to infinity lambda power k minus 1 by k minus 1 factorial. Let us call k minus 1 a dummy variable by, let us say, L, which means that k equal to 1 to infinity is the same as L equal to 0 to infinity lambda power L by L factorial, which is exactly equal to e power lambda. So, e power lambda cancels with e power minus lambda to give us lambda. So, the expected value of a Poisson distributed random variable with parameter lambda is equal to lambda. In fact, the variance is also equal to lambda. However, you have to multiply k, you have to have k squared here, you have to get e squared, you have to get k squared, and then you have to do this 2 times, but technically it is the same thing. The variance Ex squared is equal to lambda squared plus lambda. So, Ex squared minus Ex the whole squared becomes lambda. So, the variance of a Poisson is also equal to lambda. Right? And finally, we will move to the last of our distributions, which is the geometric distribution. The geometric distribution is how to motivate that. Well, let us say you are tossing a coin with bias p. Right? This is the experiment. You keep on tossing the coin until you get a head. Right? Let us say if you at the first time itself you get a head, you stop there. Right? Or you keep on tossing the coin till you get a head. The number of coin tosses you make is geometrically distributed. So, that means that x is distributed as geometric with bias p, right. So, the parameter, the bias of the coin exact is the same as the parameter of the geometric. We will say x is distributed as geometric with p if fx of k, which is probability of x equal to k. What is the probability that you need exactly k coin tosses to see a head for the first time? So, which means that the first k minus 1 times you should have seen a tail. The probability of that happening is 1 minus p power k minus 1. Why is that? Because these are k minus 1 times you should independently see a tail. So, it is 1 minus p power k minus 1, and at the kth position and the kth toss you should see a head. The probability of that happening is p. So, fx of k is 1 minus p power k minus 1 into p. So, this is the probability mass function of the geometric random variable, and x takes values in 1 to infinity. Poisson takes values 0 to infinity, integers only, 0, 1, dot dot dot. Geometric however takes values, cannot take a value of 0. I mean, the number of coin tosses can never be 0 to get a single head. The best case scenario, you'll have to still toss a coin one time. So x takes values 1, 2, 3 all the way to infinity. First of all, once again you want to check whether there is a valid probability mass function or not. We will do that. Sum over k equal to 1 to infinity 1 minus p power k minus 1 into p is equal to p into sum over k equal to 1 to infinity 1 minus p power k minus 1. So, this is a geometric series, and by standard geometric series formula this is equal to p into 1 by 1 minus p, this is equal to 1. Right. So, you have that this does sum to 1. So, this is a valid probability mass function. So, that is the first thing out of the way. Now, let us try to see if you can get the expectation of this random variable. Intuitively, what should you expect, right? So, p is the bias of the coin. So, if p is very low, right, if let us say you have a super rare, if you have a coin where heads is super rare, then you expect to toss the coin more times. So, you expect the expectation of the number of coin tosses should scale inversely with the bias. Let us see if that is really true. Right? Our intuition says that if p is very small, then you should toss more coins. So, the expected value of this random variable should be inversely dependent on p. Let us try to get that. So, what is Ex? Well, Ex is sum over k equal to 1 to infinity k into 1 minus p power k minus 1 into p. So, this is not so easy to do straightforward, because this is not a geometric series, this is not arithmetic series also. This is what is called an arithmetico-geometric series. You can use some standard tricks to get this sum. The standard trick to do that is to use differentiation of a series. Right? Let us say you have sum over k equal to 1 to infinity 1 minus p power k. What is that? Well, you know by geometric series is exactly equal to 1 minus p by 1 minus 1 minus p, which is equal to 1 minus p by p. This is a fact of geometric series. Let us differentiate this expression left and right side by p with respect to p. If you do that, sum over k equal to 1 to infinity k into 1 minus p power k minus 1 into minus 1 is equal to p squared p into minus 1 minus 1 minus p. This is u by v, this is v squared v du minus u dv. The reason you can see is obvious, that you are getting sum over k equal to 1 to infinity k into 1 minus p power k minus 1, which is the term that you want for Ex also. So, let us just multiply by minus 1 on both sides to get what we want. Sum over k equal to 1 to infinity k into 1 minus p power k minus 1 is simply equal to p plus 1 minus p by p squared, which is equal to 1 by p squared. Right. So, sum over k equal to 1 to infinity k into 1 minus p power k minus 1 is 1 by p squared. But what do we want? We want sum over k equal to 1 to infinity k into 1 minus p power k minus 1 multiplied by p. So, we have that Ex is simply equal to 1 by p, which does agree with our intuition. That is, if p is small, you expect more number of coin tosses to get to a head. You can get the variance also in the same way. You get Ex squared, but you might need to differentiate twice to get this thing. But it's a very simple logic, and you can get the variance also in the same way. But the variance is not very important here. The more important thing is that the mean of a geometric distribution is 1 by p. So, with that, you have the basic tools required for handling discrete random variables. In the next week, we will move to continuous random variables. But that is all for discrete random variables.